Okay, so I'm super excited about this talk because I have a background in optimization, and admittedly, out of the 42 years of ASMs, I missed the first 41. I am lucky to be accompanied for this conference by two young co-authors, Nora Borsik and Tamás Takács, and I would like to thank the organizers for having us here and for providing the opportunity to give this talk. We also have in our team an emeritus professor, András Frank, who could only join us online. Okay, so my definite goal for the next 30 minutes is to demonstrate how classical tools in combinatorial optimization and polyhedral combinatorics can be used to solve certain problems concerning ASMs. And I'm in a very lucky situation because most of the basics have already been covered by Roger and Liz. The only distinction I need to make is that I will use the term horizontal and vertical prefix for the set of entries that are contained in the starting segments of the rows. So these are the horizontal prefixes. And vertical prefixes are defined analogously. So this is something that Roger would refer to as partial sums, but now these are rather sets than just a number. I hope this concept is clear. And then I can jump straight to the linear program given by Péter and Knight and Slater that describe the polytope of ASMs. Here, the variables xi, j are exactly the same as in Roger's talk, but now you can see this system of linear inequalities in a slightly different form, because here we have both lower and upper bounds, as opposed to the linear program shown by Roger, where we only have lower bound of zeros for all partial sums. But for the suffixes, you can simply convert those lower bounds to upper bound on the prefixes. And if you do this conversion, then you get the upper bound 1. So this is essentially the same system that you are all familiar with. And we have already covered today several interesting properties of ASM, of the polytope of ASMs, as well as this particular system of linear inequalities. There is, however, one further property that hasn't yet been mentioned that got me and my little team interested in the world of ASMs. And this property is the following. If you consider the set of horizontal prefixes, then what you see is a family of sets, and this family is laminar. This means that any two prefixes, any two horizontal prefixes are either disjoint or one contains the other. And the analogous property holds for the vertical prefixes as well. Now, this very simple observation immediately puts us into a rather favorable situation within optimization, because linear programs and the corresponding polytopes defined by such families of sets are very well studied and very well understood. For example, by classical work due to Edmonds and Tutt, we immediately get that the matrix of the linear inequality system by Péter, Knight, and Slater is a network matrix. Network matrices are known to be totally unimodular, and as the right-hand side, so the bounds were all integers, we immediately obtain that the polytope defined by this set of linear inequalities must be also integral, which in turn means that it describes the convex hull of ASMs. So if you like, this was a two-sentence proof of the fact that this system describes the polytope of ASMs. Such linear programs are known to define polytopes, which can be obtained as component-wise projection of so-called circulation polytopes, which in turn opens the door toward using classical theory of network flows. And we also realized that the polytope of ASMs is the intersection of the so-called laminar generalized polymatroids, which again are very well studied and have a rather deep theory. So what we have now is 3 different approaches, each giving its own perspective and a distinct set of tools for analyzing certain problems, and in particular the polytope of ASMs. And what we noticed was that these 3 approaches had a common trait, namely that none of them assumes anything about the bounds that we have on the partial sums, maybe except that they must be integers. This is the only only assumption that we made. And this immediately led us to the introduction of our key notion, Prefix bounded matrices, which are defined as follows. We are given 4 matrices. Each of them is of dimension m by n, and their entries are all integers. And we say that an m by n integer matrix X is a prefix bounded matrix, or PBM for short, if for every row index I and for every column index J, we have the following properties. The J special strand of row I must fall between phi 1ij and gamma 1ij. And the analogous requirement is posed for the vertical prefixes or vertical partial sums as well. Here the bounds are given by phi 2ij and gamma 2ij. This immediately gives rise to a natural system of inner inequalities. This is again defined by 2 laminar families of sets. So again, this natural system of inner inequalities in the n by n dimensional real space describes the convex hull of PBMs. This is no longer a polytope because we can have large entries in PBMs, but still a polyhedron. And we will push things just a step further. We consider the same set of inequalities, but also pose lower and upper bound f and g on every single entry, and also on the total sum of the entries. Here the ones will be alpha and beta. We will again assume that all of the numbers are integers, all of the bounds are integers. And again, this system is still defined by 2 laminar families of sets. So again, they describe the convex hull of the PBMs for which the entry bounds f and g and the total sum bounds alpha and beta are satisfied. The notion of PBMs is generally enough to capture several notions that I actually learned during this week. Of course, ASMs are a special case, which correspond to the case when the lower bound on the horizontal partial sums, or horizontal prefixes, is uniformly 0 except for the full rows, but it is 1. This transposes the bound on the vertical partial sums, vertical prefixes, and we have a uniform bound of 1 for every partial sum. This is just the bound. These are just the bounds for ASMs. So if we plug in these exact bounds to the polyhedral description of PBMs, then what we get back is exactly the system of parameters. Another case that already learned up during this week is the notion of partial ASMs, Fourier and Stryker. These are exactly the PBMs that satisfy the uniformly 0 lower and uniformly 1 upper bound. Rectangular ASMs correspond to this setting. Here the lower bound on the vertical prefixes or vertical partial sums is changed to uniform 0. Alternating sign triangles that were already mentioned in the talk of Fisher on Wednesday correspond to exactly PBMs for these bounds, except that their shape does not quite fit. And this is where our entry bounds f and g become useful, because we can simply froze the bottom left and bottom right triangles to 0 by forcing the lower one of 0 and letting the entries within the triangles to be at least -1. And similarly, setting the upper bound of 0 on these triangles and forces those ends to 0. And therefore, you can see that this essentially captures alternating sign triangles as well. Higher spin ASMs. These already bound up in the project this morning. These are just the air dilations of ASMs, correspond to this set of lower and upper bounds. Irregular ASMs were introduced by Druard and Dahl, and they are, again, essentially the same as higher spin ASMs, except that now we restrict ourselves to the -1, 1 cube. So for every entry, we describe the order -1 plus 1. And probably there are several other special cases that I am not aware of. For example, such a case is the case of mixed alternating sign matrices. Those can also be captured by similar bounds, but that was enough about the special cases. And now let's turn back to PBMs. Recall that we could pose any lower and upper bounds as long as they are integers. So a very basic question is whether for given bounds there exists a PBM or not. It may happen that it doesn't exist. So the question is whether for our bounding matrices phi1, phi2, gamma 1, gamma 2, there exists a PBM that also satisfies our entry bounds f and g and total sum bounds alpha and beta. And here is the characterization. Such a PBM exists if and only if for every two subsets x1 and x2 of the positions of our n by n matrix, we have the following four inequalities satisfied, where f tilde of z is just defined as the f sum of the elements of z. G tilde is defined analogously, and P star and B star are the strongest lower and upper bound implied by our bounding matrices pi and gamma. So in a sense, this is an extension of our bounding matrices from partial sums to the sum of any subset of the entries. You can give a simple sum formula for these, so this can be explicitly defined. And so if one finds such subsets x and x2s, so that one of these four inequalities does not hold, then it certifies that no PBM exists. For example, if this first inequality is not satisfied, then what we have on the left-hand side is a lower bound on the sum of the entries in x1 and in x2. The reason being that P star 1 x1 is just a lower bound on the sum of the entries within x1. The sum of the f values on its complement x2 minus x1 is again a lower bound on the sum of the entries within that set. So these together give a lower bound. Similarly, you can argue that the right-hand side is an upper bound on the same quantity. So if this inequality is violated, then what we have is a lower bound that's larger than an upper bound. This clearly is a contradiction and certifies that there is PBM. Okay, I will admit that this system is a bit cumbersome, but if you specialize it for the case of ASMs, then things become much more digestible. The problem we are going to consider is this. We are given a partition S of the positions of an n by n matrix. This will be our ASM. And this partition consists of 6 parts, which you can see here. We say that an ASM X is S compatible if the following 6 conditions hold. For every position Ij that's within the part S minus, the entry at that position must be non-positive. For any position that's within the part S plus, that entry must be negative. And for every k equals 0 plus 1 minus 1, if your position Ij is in the part Sk, then its value must be exactly. And you may notice that SF is nowhere mentioned. The reason is that we do not have any constraints on those entries. So the letter F stands for free. These are the constraints. And the question will be whether there exists an S compatible ASM. Here is an example. Does there exist an ASM that has a -1 in the middle? This for S consider the case when S minus 1 consists of the only position U2 and the rest of the positions are in SF. And of course, the answer is that there is such an ASM. Here is a more complicated challenge for you. Here, this sign plus indicates that this entry or the position of this entry is in S plus, so this must be in negative, and this other one is in positive. And of course, given values are this. Question is whether such a ASM exists. This is much more difficult than going to try to convince you that no such PBM exists. Consider these 5 segments. Segment is just a set of contiguous entries, either horizontal or vertical. And notice that within any such segment, not just this 5, but any segment, the sum of the entries can be at most 1. This is by properties of sums. So for the entries covered by these 5 segments, we have for the sum of the entries covered by these segments, we have an upper bound of 5. And for the rest of the entries, those 7 entries that aren't covered, we either have a prescription of 0 or are prescribed to be non-positive. Therefore, we can upper bound their sum by 0. So this means that the total sum was 5, which is still fine because the total sum on ESM would be 5, because this is a 5 by 5. But notice that if you consider these 2 segments, then at their intersection, there is a 1 prescribed. This means that every other entry covered by these 2 segments must sum up to at most 0. And therefore, the sum of the entries within these 2 segments can be at most 1. Therefore, we can sharpen by outbound by 1 and obtain an upper bound from the total sum of 4. But that's a contradiction, because a 5 by 5 ASM sums up to 5. And the good news is that such a certificate and the similar argument always justifies if no PBM exists. Before I can say the exact theorem, we need just one last definition. We say that family of separated segment is just a family of vertical and horizontal segments, such that any 2 segments in the same row or column must have an entry between them. They cannot touch each other. For example, this is not a family of separated segments. The reason being that these 2 vertical segments don't touch each other. There is no entry between them. But if we make the bottom one by one shorter, like this, then what we obtain is a separated segment. And here is the characterization. There exists an S-compatible ASM if and only if this inequality holds for every family I of separated segments that fulfills certain covering properties, namely every entry in SF must be covered exactly once, the entries in S minus union S1 at most once, and the entries in S plus union S plus 1 must be covered at least once. We also define two sets. I0 will be the set of entries that aren't covered by all, and I2 will be the set of entries that are covered exactly twice by the system of segments. And what we have in this inequality on the left side is n, which is the total sum of the entries in an sum. On the right-hand side, we have the cardinality of our families, the number of segments we used. And this can be deduced if we have entries which are covered twice. This is something that we have just in this example. A similar phenomenon happens if we have an entry prescribed to be -1 that isn't covered at all. And so if you can find a family I of separated segment that violate this inequality, then you have a certification that you may wonder what gave rise to this characterization. And somewhere very, very deep behind the scenes, but essentially happens is that the linear inequality system of Bear and Knight and Stryker is TDI. This stands for totally dual integral. This was a conjecture by Edmonds and independently proven by Walter Morris, unpublished work. This essentially means that you always have an integral dual solution. And this provides the opportunity to give a complete interpretation of the dual program. What you can see here is this interpretation. And the non-trivial part is to somehow realize that there is such a combinatorial meaning behind the dual program, which is just again a set of inequalities. So we obtain this as a special case of characterization of the existence of PBMs. But even this special case has special cases that are of interest. For example, throughout the entire call an n by n matrix A to be, or say that it is a subordinate of an n by n matrix X if our matrix A can be obtained from X by replacing some non-zero entries with zeros. And they ask this: when does a matrix X that has only 0 plus or minus 1 entries have an ASM subordinate? And here is our answer, which is just a special case of the previous theorem, as I will soon explain. So a matrix X has such an ASM subordinate if and only if one cannot cover the class 1 entries of X using pure and separated study, making sure that each minus 1 entry is covered by at most one of the segments. So this is the characterization, and we can prove this together if you realize that if we have an entry 1 in X, then it just means that in the ASM we are trying to find that entry must be non-negative, because you either leave that entry at value 1 or change it to 0. This just means that it must be non-negative. So this is very well captured by S compatibility problem. And I forgot to mention that the same analogous statement holds if an entry is non-positive. Now you have a non-positive. This is the special case. Another problem that came to my mind during the talk of Alamo yesterday. I call this ASMs with those entries. You can guess what this will be about. When does an ASM exist with a set of entries prescribed to this question? And of course, this is just the special case from every part other than S0 and S are empty. And our characterization then simplifies to this: that exists such an ASM is if and only if for every family I of separated segments that covers the entries in the positions, exactly ones, the size of the set of segments is at least 1. This is the characterization. I am going to turn now to two structural results, which will be implications of classical results in cognitive relaxation. The first one concerns the decompositions of irregular ASMs. Irregular ASMs, something that I already mentioned, corresponds to the special case of PMs for these bounds. These are considered by Duarte and Dahl, who proposed the following conjecture: for every such irregular ASM, there should exist pairwise pattern disjoint ASMs, A1, AK, such that they sum up to A, and they must be pattern disjoint. The pattern of a matrix is just the position of the entries that are non-zero. So essentially, this says that the support of these ASMs should be disjoint. And the answer is that this conjecture is true, and without the pattern disjointness requirement, what we have is equivalent to the integer decomposition property of the irregular ASM polytope, which is implied by the fact that that polytope is defined by a system whose matrix is totally modular. In order to somehow enforce pattern disjointness, we had to tweak it a little bit and define the notion of sign consistent integer decomposition property. But this was more like a technical difficulty than a real problem. So essentially, this conjecture is busted by a classical result. It's the decomposition of polytopes determined. We have already know the characterization of the vertices of ASMs, and I'm going to generalize this and extend to several other related notions or classes of matrices. Here is the setting. We have a polytope P, which is the convex hull of certain 0 plus minus 1 valued n by n matrices. The requirement is that the non-zero entries must alternate in every row. And we also need to specify the value of the first non-zero either at the beginning or at the end. This is the requirement, not its position, but just its value. And then if you take any polyhedron Q, then in the intersection of P and Q, every integer element must be a vertex of the intersection. Now, this is a one-directional statement. So this says if you have an integer vector within this polytope, then it must be a vertex. It still may happen that there are rational vertices. Nevertheless, if we set P to be the sum of the entries, to describe the system that enforces that the sum of the entries in each horizontal prefix is 0 and 1, and we set Q to enforce the ASM condition for each column, then what we get is the well-known statement that the ASMs are exactly the vertices of the polytope. The reason being that we know that P intersection Q is exactly the data cycle system, and it does describe the combustion of PSMs. So every vertex must be integer. And if you tweak a bit with the definition of P and Q, then you obtain the analogous statement for partial ASMs, for rectangular ASMs, for alternating sine triangles, or for network matrices, and again, possibly by other classes of matrices. The main requirement is that there must be an alternating direction, either rows or columns, it doesn't matter, but there must be one. And the other constraint doesn't really matter, at least from this perspective. Okay. You may wonder if these characterizations can be addressed algorithmically or not. So if I give you a PBM or give you a partition S, and ask whether an S-compatible ASM exists, can you find such a PBM? And if it doesn't exist, then can you give the certificate that it doesn't exist? And you may also wonder if, given a key-regular ASM, we can generate or find its decomposition into ASMs or not. And the answer is 3 yeses, or maybe I should say 9 yeses, because all 3 approaches provide a yes answer for all of these 3 questions. So you have a lot of flexibility here. Probably the easiest approach is that you can always boil down such problems to finding certain flows in this field. Thank you for your attention.